All right, we want to talk today about how do we determine if a set of data is normal. And that's going to be a really important topic as we move throughout the year. We're going to talk about some ways that we can do this by looking at the set of data today and determine if a set of data is normal. So you should have talked already, and hopefully you're able to brainstorm some ways or some things that you need for data to be normal at the very least, or some ways that you could tell if this data was normal for both the heights of men and the heights of women in 57 different countries around the world. Now I have in here already inputted my data for men and for women. And we're going to take a look at the men's data first. Okay? So the first thing that a lot of students think of is, okay, well, what do I know about a normal distribution? And that's that it's symmetrical. And if it's symmetrical, then the mean and the median should be the same or approximately the same. Very rarely will they be exactly the same. And so one thing that students tend to do is they go, okay, well, let's calculate the statistics for the men. Okay, and my frequency list is just blank. I'm going to calculate. Okay, and so here's my mean, 172.4, and my median is, pull this over here, see if we can get this to work better this time. I was having trouble with it the first time I tried to do this. Okay, so the mean is 172.4, and the standard deviation is 6.5. And if I scroll down here, I can get the median. The median is 171.5. And we go, whoa, that's actually really close. That number there and that number there are really, really close to the same thing. They're off by just under 1 inch or 1 centimeter. Okay, so the mean is approximately equal to the median. X bar is 172.4, which is approximately equal to 171.45, which is the median. Okay, and so the X bar and the median are approximately the same. However, there are lots of distributions that are that have their mean and their median the same. For example, a uniform distribution would have the mean and the median being the same. Okay, an inverted curve would have the mean and the median being the same, like something that looks like a parabola. This would be the median. If this was our density curve, this would be the median, the 50% point, and it would be the balance point, the mean. Okay? So there are lots of different curves that would have this. And so just having the mean equal to the median is necessary, but not sufficient. Okay? In other words, we can certainly determine that a set of data is not normal if the median and median are not close together, but we cannot say that because the mean equals the median that the data is normal. Okay? So we got to go a little bit more in depth here. Well, what if we graph it? Okay, well, let's do this on our calculator. Let's go to stat plot, and I'm going to go with plot 1 here. And I want the histogram. We're going to start with that one, the histogram. And I'm going to do this for the men. So second list. The mine are not named like L1, L2. This is the men's list. Frequency of 1. And now I'll go zoom 9. Oops. Oh, yeah. It doesn't like that. Okay. So quit. And now I'll go to zoom 9. Zoom stat. And I get a set of data that looks something like this. So, well, let's see that shape. Does that look normal? Well, yeah, maybe a little bit of right skew here, but in general, that looks pretty normal. Okay, I know I'm kind of rough-handing that sketch in there. It's not a perfect normal curve by any stretch of the imagination, but okay, that looks roughly normal. And maybe we could get an even better idea if we set our values so that they are centered around the mean. Okay, So our mean here was, let's keep this in mind. I'm going to pull this over to this side so I can see our mean and stuff. Our mean was 172.4, and our standard deviation was about 6.5. So I'm going to go back to my window here. And I'm going to have the X minimum start at like 4 standard deviations to the left. So I'm just going to type in here 172.4 minus 4 times the standard deviation. When I hit enter, it's going to automatically calculate that. Now the X max, I don't really need to do, but if you want, if you really want it to be centered and stuff, you can do 172.4 plus 4 times the standard deviation. 198.4. Okay, now here's the really important part, the X scale. Because what the X scale does in a histogram is it sets the bin width. It determines how wide the bins are. And so I want that to be the standard deviation. So that basically I'll start at the minimum value and I'll go over a standard deviation for each bar. So I'm going to set that at 6.5. And now my Y max, I'm probably going to have to move this up. So I'm going to guess like 23. And there you go. Okay. Now what's happened is we've got data. We've got our data centered around the mean. Okay, so that this is our mean right here in the middle. This is X bar. Oops. Okay, this is 1 standard deviation above the mean, X bar plus S. This is X bar plus 2S, and same thing going the other way. So this is X bar minus S and X bar minus 2S and X bar minus 3S. And you'll notice that it looks like within 3 standard deviations, and this is X bar plus 3S. Within 3 standard deviations, we have all of our data. Okay. But this curve, this looks really symmetric, right? And it looks bell-shaped. Okay. It's got a peak in the middle. Looks kind of like a bell curve. You can kind of sketch in a bell curve and say, yeah, that looks like a bell curve. I mean, that looks like what we would expect to have happen. Okay. What about some numerical evidence? This is graphical evidence. So that's one way we can do it. We can graph it and say, you know, does it look like a bell? You know, and there are other graphs, right? Just really quickly here, if we were to change our stat plot to a box plot, that's another one. Okay, I'll do the box plot with outliers here. We hopefully don't have any outliers. Zoom 9. There's our box plot. Okay, and a normal curve does typically look something like that as a box plot. You've got larger whiskers than you do boxes. So the first and fourth quartile are more spread out than the second and third quartile. And the reason for that is that if you think about a bell curve, right, your middle 50% is within, I mean, less than a standard deviation away, right? 68% should be within 1 standard deviation. So 50% will be within less than a standard deviation. And this outside 25% then will go from like right here over, and the top 25% will go from like right here over. So there's a lot more spread in those 2 whiskers. Okay, so a box plot that's normal, you're not necessarily looking for everything to be equal, but typically you would have longer whiskers and you'd have shorter widths on your boxes, on your middle quartiles. All right, what about numerical evidence? Well, let's use the empirical rule. And having set up my histogram already in such a way that it counts by standard deviations, it's really easy for me to figure out where my standard deviations lie. X bar minus S to X bar plus S, X bar minus 2S to X bar plus 2S, and then X bar minus 3S to X bar plus 3S. Okay. Well, let's figure out what those values are. Right. So if I go back to, oops, I'll have to go back to, oh no, I'm going to change my window back. 172.4 minus 4 times 6.5. And this was like I don't know, I will call it 195. That one doesn't really matter, but it bases it off the X minimum. So it starts at the X minimum and then it adds whatever your scale is. All right, so let's graph that. Let's see what happens here. Oops. Change it to a histogram. I'm still thinking. There we go. Change this to a histogram. So now let's graph it. See, there we go. All right, so there's our data. Let's go trace. And that bin over there had a value of 0. That was 4 standard deviations away. This bin goes from 152.9 to 159.4. So those are the lower bounds. 152.9, sorry, that's 3 standard deviations away. And 159.4 is 2 standard deviations away. Right. And if I go over here, now you notice there were 2 values there. We'll keep that in mind. We'll count those up here in a minute. 165.9 then is 1 standard deviation away. You'll notice that next value there, the middle, the maximum of this bar is 172.4. That's our mean, more or less. And so now at 1 standard deviation, goes from 172.4 to 178.9. This would be to 178.9. And then 178.9 to 185.4. So 185.4 is 2 standard deviations above the mean. And you could do this by hand too, right? You can calculate all these out. 191.9 then. So 191.9. So within 1 standard deviation would be anything from 165.9 to 178.9. You could count those out on the paper. If you sort the data, you could sort in ascending order and then select your list that you want to sort. It'll put that data in ascending order. So when you go to stat, edit, it'll go from least to greatest. Or the easiest way here is let's just look at the heights of these bars. Oops, trees. So the middle 2 bars are 19 and 19. So that's 38 out of 57. Okay, we'll calculate that here in a moment. If I add the next outside 2, we've got 8 over there and 7 there. So add another 15 to 38. That's 53 out of 57. And then the last one, well, that was 100%, right? I mean, we can show here that's 2 more. And over here, that's an additional 2 more. So that's a total of 57 out of 57. So that's 100%, which is pretty close to 99.7%. You're not going to get any closer than that with 57 data points. 53 out of 57. Now, if you remember, 2 standard deviations away should be 95% of the data. 53 divided by 57 is 93%. Which that's really close to 95%. 2% off, that's not bad. Okay, we're like 1 data point away from that being like golden, perfect. Okay, and it's not going to be perfect because it is data. And then 38 divided by 57 is 66.7%, which is really close to 68%. Again, you're probably not going to get any closer than that. Maybe if you have 1 more. And so from the empirical rule, our values, right, match or close to match the empirical rule. And we get percentages that we should. Okay, so there's another way you can do it. One other way you can take a look at this is there's another graph on here that's really helpful. Okay? And if you go to stat plot and you edit the very last choice here. So you choose one of your plots. This right here is called a normal probability plot. Okay? And what it's going to do is it's going to calculate the z-score for each of the data values. And then it's going to plot, the way I have it set up, it's going to plot the data value, the height, as an x value, and the z-score for that height as the y value. So it's going to plot those coordinates for each of the points. And let's take a look at what we get here. Okay? Now, whatever we get, it should look pretty normal. we get a graph like this, and this looks really normal for a normal probability plot. Okay, a normal probability plot won't look like a normal curve. If data is normal, then the normal probability plot should be very linear. Okay, in other words, all of your points that plot the data against their z-scores should provide something that's really close to a line. And we're looking for not little wiggles away from a line, but a major departure from a line. And there are no major departures from a line here. And all these data points line up pretty nicely. This is a pretty nice set of data. And so that would be another way you can do it. So let's look for a minute here then at the women's data. Sorry. All right. Let's look at the women's data. I have that data in here as well. Now we won't go through and calculate, number of values within 1, within 2, within 3, but let's just take a look at a couple of the graphs. And then I want you to talk about why the difference, if there's a difference, or why we would anticipate them to be the same if they're the same. So I'm just going to change this to the women's list. Okay. And I'll quit to go home. Zoom 9. Stat. That looks fairly symmetrical. There's a little bit of a skew to the left, but there's not a huge skew to the left here, so fairly symmetrical. What about the normal probability plot then? Well, let's see here. Second stat plot. And now we'll go back to Zoom 9. You see something that's not quite as linear either. You kind of see how those match up. The graph had a little more skew to the left. Got a little bit more of a bend, so the curvature opens upward here. The curvature of this graph opens upward. Oh, I won't need it over here. There we go. Okay, so we get a little more curvature here, opening upward, up like a cup. All right. Looks kind of like part of an x squared graph, y equals positive x squared. And that's due to this little bit of left-hand skew here. Okay, now is that enough? Is that one value essentially that's too low, or two values that are too low, worth our time? Well, I don't know. I wonder, did it change our x values? What was, yeah, it did, it changed the x scale here when we graphed it. Okay, so I'm not concerned about the standard deviation messing anything up there. So I want you to talk in a little bit here. We're going to summarize this, but I want you to talk about why would there be a little bit of left skew in the women's heights versus the men's heights, as just a little bit of discussion. But just to wrap things up here, how do we determine if a set of data is normal? Okay, well, you got to do one or more of the following. Okay, now the first one we saw was the mean is approximately equal to the median. Oops, approximately equal to. There we go. And this is necessary but not sufficient. Okay, so you can say that something is not normal because the mean and the median are not the same, but it's not sufficient to prove that they are. Okay. You could take a look at the graph of the histogram. Or a dot plot, or a box plot, or stem plot. Usually we do a histogram or a box plot because the calculator will do that for us, right? And just look at shape. You could use the empirical rule. (68, 95, 99.7). Right? Go to one standard deviation on each side is 68% of the data there, about 68%. Is about 95% within 2 standard deviations. Is about all of the data within 3 standard deviations. And then the last one is a normal probability plot. And we want something to be roughly linear. If it's normal, the normal probability plot will be roughly linear. So go ahead and discuss a little bit, like why is there a little bit of left-hand skew there? Look at which countries are causing that skew maybe, and talk about what you know about those countries. And then take a look at the in-class practice. Okay? And I will post these notes on Canvas so that you can check your answers when you're done. Okay. And I will see you in class later this week.